Hi everyone. So this is going to be a lesson about the product rule and the quotient rule. And these are going to be two rules that allow us to differentiate a ton of new problems. Things that we haven't been able to differentiate yet will be possible after these two rules. Okay, so let's go ahead and get started. So these are two separate rules, the product rule and the quotient rule, and we'll talk about both of them. We'll see example problems that use both of them. Because these rules are so important, I do want to spend some time deriving them to see where they come from. But before we do any of that, let me show you a type of question to try to convince you of why we need some kind of new rule. So, question. What if we're given h of x, it's capital h of x equals x squared e to the x. What is h prime? What does h prime equal? And I guess the message that I want to get across is, first of all, just so you know, I'm not asking you to solve this problem right now. This is something we need to spend some time on. We know how to do the derivative of x squared, and we know how to do the derivative of e to the x. So do we just find the derivative of the first piece and the derivative of the second piece? I'm like actually asking that as a question. Like, is that what we're supposed to do? Here, I'm going to underline. There's like the first piece and the second piece. Well, we've never really had this situation before in this class. We've had this situation with a plus sign in between, and we've had this situation with a minus sign in between, and those problems would be a lot easier. If this was x squared plus e to the x or x squared minus e to the x, then yeah, you just handle each piece individually, and there's no problem. This is multiplication, right? This is x squared times e to the x. So this is a product of two functions. And I guess I'll tell you, we don't just differentiate each part. If you just differentiate each part and put them side by side, it's going to be the wrong answer. And we're going to derive a new rule, and it's going to be called the product rule, that's going to help us get the correct answer. So in general, not just for that problem, but if we have a function called h of x and it equals a function times another function, what is the derivative? I'm using capital H because I want to use f and g as the two smaller pieces, the two functions that are getting multiplied times each other. So for my main function, I wanted to use a different letter, so I'm using h. And I used capital H because, in the derivative, we use a lowercase h already. So I used capital H here. We're going to derive a rule, and we're going to get there by trying to use the definition of the derivative. And we're going to see what happens, because the definition of the derivative formula should always be true. So technically, that should always work. So this would look like this. Minus h of x, all of that over lowercase h. All right, so what's capital H of x plus h? Well, in this case, capital H is f of x times g of x. So put x plus h in place of x. So this is going to be f of x plus h times g of x plus h minus f of x times g of x, all of that over lowercase h. And we need to figure out something to do with this to simplify it, because there's not really anything that we can cancel right now. Okay, we're going to use a clever trick here. A lot of times in math, when we derive things or we prove things, there are some clever tricks that are sort of hard to come up with from scratch. And I wouldn't ask you to come up with this step from scratch. But hopefully once you see it, you'll at least be able to say, okay, I could see why that's true. So here comes the clever trick. We want to do something with this numerator. And there's nothing really that we could factor out or expand or cross out or anything like that. What we're going to do is, here's the first piece. I'm going to subtract f of x plus h, g of x. I'm going to add f of x plus h, g of x. And minus f of x, g of x. All of that is over h. Now, I'll explain what I did here. This looks like the previous line, except for this stuff. What did we do? We add and subtract the same thing. Right? There's an expression, f of x plus h, g of x, that we have added and subtracted. So that's weird, because why would you do that? If you add something and you subtract it, then it's like you haven't really done anything. And it might not really be clear yet, why is this going to be useful to us? It is going to be useful to us, but you should at least be able to see that this is allowed, like that we didn't do anything wrong here. It's kind of like if you had some kind of expression and you decided to say, you know, I'm going to do plus 5 minus 5. It doesn't change what you had if you do plus 5 minus 5, right? It doesn't change what we have if we do plus this minus this. So these lines are still equal to each other. The cleverness about this is going to come up in the next step when we start grouping terms together. So what I'm going to do is I'm going to have f of x plus h, big parentheses, and I'm going to pull the g x plus h and the minus g of x. Close those big parentheses. So I'm not done yet with the numerator, but I have this first term and this second term where I've factored out f of x plus h. Then I'm going to have plus, we still need these other two terms. What do they have in common? They have g of x in common. So we're going to have g of x pulled out, big parentheses, f of x plus h minus f of x. So it might look like we've taken the problem and made it more complicated. And that's true, we have, but we kind of had to. It's going to get simpler though. So you should see that that does equal the previous line. What do we do about this gigantic limit? Well, we have a property of limits that says, you know, a limit with something with a plus sign in the middle can be split up into two limits. I'm going to split this up according to some limit properties, okay? First of all, I could take the limit of f of x plus h, just that, and make that one piece. And then I could have the limit of h goes to 0 of g of x plus h minus g of x over h plus, let's do the limit of just g of x times the limit of f of x plus h minus f of x, all of that over h. So if you look carefully, this is also equal to the previous line. Use limit properties to break up some sums and products of limits into, instead of one limit, we now have 4 limits. Breaking it up into pieces is sometimes good. All right, guess what? These 4 pieces that we broke it up into, we're going to look at each one of them individually and figure out what they are. Some of them are easy. Actually, none of them are really too hard. So, the limit of f of x plus h as h goes to 0 is just f of x, because the h goes to 0. The limit as h goes to 0 of this piece, g of x plus h minus g of x over h. You know what this is? You know what this is? This is the formula for g prime. That's exactly g prime of x. We have a big plus sign in the middle. It's still there. That worked out nicely, that was just the derivative of g. Okay, over here, as h goes to 0, g of x is still just g of x times, what's all this stuff? Limit h goes to 0 of all this. This is exactly the definition of f prime of x. So we've reached a result. We've reached an answer. And this is it. So we call this, we just derived the product rule. And it says, let's summarize, if h of x is f of x times g of x, a product of 2 functions, then h prime of x is equal to what we found, f of x times g prime of x plus g of x times f prime of x. So the product rule is this formula used in situations when you have a product of 2 functions. So thinking back to the question that I asked at the top of the page, you know, I was saying, is it okay to just take the derivative of the first piece and take the derivative of the second piece? Unfortunately, it's not that simple. That would get us the wrong answer. This will get us the correct answer. So we need to know the function, the derivative of the second one, and then the second function, and then the derivative of the first one. I'm calling these two things like the first function and the second function. So there's 4 pieces to this puzzle. First function, derivative of the second one, second function, derivative of the first one. There's some other ways that you could write the product rule. You know, sometimes we like to use the ddx notation. So we should be able to be comfortable with this notation also. So this would say, if you have to do ddx of product, f of x times g of x, that it equals f of x times ddx of g of x plus g of x times ddx of f of x. So there's no prime symbols in this one. Instead of prime, we've done ddx. Or sometimes I've seen people write this formula in like a more compact way just to help remember it. I've seen it written as something like fg prime equals f. So there's fg prime in parentheses equals fg prime plus gf prime. That's, I guess that's about as compact as you could make it. I usually don't write it that way, but if it helps you remember it, then sure, go ahead and do it that way. It's basically what we wrote. It just doesn't have the parentheses x, right? F parentheses x, G parentheses x. All right, so here's what we're going to do. We're going to go back to that problem that I posed at the top of the page, and let's finally answer it. So, example, given h of x equals x squared e to the x. What is h prime? And, you know, at the top of the page, I kind of underlined each piece. I do that sometimes as a sort of scratch work to quickly identify what are the two pieces of this problem. You could do that if you want. You don't have to. The little underlines. But according to the product rule formula, if I think of x squared as f and e to the x as g, then what I need is I need f of x times the derivative of the second function plus sine the second function times the derivative of the first function. We still have a little bit of simplifying to do, but I just want to indicate that this was f, this is g prime, this is g, this is going to be f prime. So I'm following the product rule formula. And we still have to do these little ddx problems, right? These little derivatives. But these little derivatives that we've got are easy. X squared times e to the x, because e to the x is its own derivative, plus e to the x times derivative of x squared is 2x. So we basically did it. I think I would probably rewrite this answer, though. I don't like that. I don't like where that 2 is. It looks weird to me to have e to the x times 2x because 2 is a constant, and we would usually move a constant to the left and put it out front, right? Instead of having it in the middle, e to the x times 2 times x. Look, it just looks off to me. So I want to move the 2 to the left. While I'm at it, I'm also going to bring the x with it. So I'm going to write this as 2x e to the x. Typically, we like to do this sort of order because it's just considered a little bit more readable to have things like x or x squared to the left of the e to the x because it makes it clear that e is only being raised to the x instead of having other stuff to the side of it. It's easy to see 2x e to the x. All right, so I'm going to put a box around this and say that's the answer. A little more complicated than maybe we would have thought. You might have looked at this problem and you might have said, you know, well, derivative of that is 2x, derivative of that is e to the x. So you might have been tempted to just say the answer is 2x e to the x. It turned out that that's part of the answer, but that's not the whole answer. This is the whole answer. Oh, by the way, if you want, this is optional, but you could look at these and you could say these two terms have some things in common. So maybe you want to factor out x from both pieces, and maybe you could even factor out e to the x from both pieces, and then you get x e to the x, x plus 2. So I'm saying that that sort of thing is optional, but you could write the answer that way. Cool, so we've established the formula for the product rule. We've done one problem, and we want to spend some time doing some more problems. By the way, before I move the page, I'll just tell you that the product rule formula, it's an important formula. You're going to want to know it. The original function that we're taking the derivative of, it doesn't have to be called h, right? It could be called y, it could be called h, it could actually be called f. What if the main function that we're dealing with were called f? We could still use this. We just have to be a little careful about, you know, f's and g's and things like that. I'll show you this in the next problem. We don't want to have to call all of our problems h from now on. That would just be awkward if, like, from now on, all functions must be called h. No, so we're going to say that you're going to see problems where you're given something that's called f, and it needs the product rule. So I'm going to do this one for us, and we want to find f prime. I'm going to move the old problem out of the way. Okay, so, note the function can be called f instead of h. It's still something that I identify as a product rule problem because it does have like one piece times another. There's kind of a function here and a function here. Do we want to call them f and g? Well, if I call them f and g, then it gets a little confusing because if you call this first piece f, well, the whole thing is supposed to be called f. So I guess what I want to explain here is that we can use the product rule without specifically calling this f and calling this g. We could just think of it as the first function and the second function. And then we never have to worry about like using a duplicate letter. So I'm going to refer to this as the first function, and that's the second function. And we're going to find f prime of x. The product rule says that we want to take the first function times the derivative of the second one plus the second function times the derivative of the first one. Okay. Derivative, here, let's just do these little derivatives right here. This thing here is 1. And this thing here is, so, derivative of x is 1. Derivative of e to the x plus 1 is e to the x. So altogether, we get e to the x plus 1 plus x e to the x. And that's my answer. Or there's probably some other ways that you could write this. You could kind of group some things together. E to the x, x plus 1 plus 1. That's also equal to what we wrote. By the way, before we move on, I'll say another way that we could have done this problem is instead of applying the product rule right away, we could have distributed first, just algebra first, like distribute across the parentheses. And then we would still have to use the product rule for part of it. So I think it would wind up being about the same amount of work anyway. But if you wanted to do that, you could do that and you should still get the same answer. Okay, so I'm going to give you a problem to try. Let's see, given, we're going to call this one y. Let's call the function y. Y is e to the x square root of x, and I would like you to find y prime. So take a minute and try that, and maybe pause the video and spend some time on it. So what we should get is that y prime is the first function times derivative of the second one. What's the derivative of the square root of x? Well, a lot of times when I see the square root of x, I like to think of it as x to the 1/2. So let's just do that. For the part where we're taking the derivative of it, I think that's going to help. Then I need the second function times the derivative of the first. Okay. So e to the x times, let's do this, d dx of x to the 1/2 is 1/2 x to the negative 1/2 plus, I can see right here that we're going to get, well, we'll go ahead and write it. Square root of x, e to the x. I'd like to rearrange this and fix this up a little bit. I guess, technically we did find the derivative, but it's just not in a very neat way of writing it. The 1/2 I'd like to pull out front. I think I'll take the x with it. So maybe like 1/2 x to the negative 1/2 e to the x plus this thing here. I don't like a square root of x followed by something else, because sometimes in handwriting it can be hard to tell where does the square root end. I think I made it pretty clear that the square root is only over the x, but you'd be surprised how many times I see people write and it's just not clear. Is the square root over just the x, or is it over the whole thing? So in order to sort of remove that ambiguity, you can just change the order. And now nobody can second guess you. Nobody can say, oh, how far does that square root sign go? It's very clear that it's not, the square root sign is not over the e to the x part. So we could leave it like this. Let's see, is there any other way that you might have gotten this? I guess you could pull out e to the x. You could do something about the x to the negative 1/2. So another way that you might get this is e to the x 1 over 2 to the square root of 2 times square root of x plus square root of x. That's also equivalent to what I got. Either one of those looks fine to me. I'm going to give you one more to try for now. Getting used to doing the product rule. All right, so given f of x equals, wait till I write the full problem here because I want to say something about it. Given f of x equals x cubed e to the x, find f double prime. The thing that I wanted to say about it is I just want to point out that this problem is asking you for the second derivative. So don't overlook that. This says f double prime. All right, go ahead and take a minute and see what you can find for that. Okay, this is a good problem. If you can get this one, then you're probably getting pretty good at the product rule by now. First, I'm going to do the little thing where I underline each piece. I'm going to say there's my first piece, there's my second piece. I guess I didn't do that in the previous problem. It's a scratch work type of thing, and you don't always have to do it. It's up to you. All right. F prime. Why am I finding f prime? We want f double prime. Well, it's because we need to find the first derivative before we can find the second derivative. So this is going to be x cubed times the derivative of the second piece plus the second function times the derivative of the first one. So I've applied the product rule formula, and that's going to get me x cubed e to the x plus, I can see that the derivative of x cubed is 3x squared, and I'm going to go ahead and write that out front because I have a feeling I would write it and then I would just rearrange it in the next step anyway. So this is the first derivative. If the problem said f prime, then we would be done, but the problem said f double prime, so we have to keep going. It wants the derivative of this. So what do we do? Well, we could just treat each one of these pieces as like a separate problem, right? We want the derivative of x cubed e to the x, and we want the derivative of this other one. And to find the derivative of the other one, I decided to just pull the 3 out. You could leave the 3 on the inside. It would still work out. In the end, it would be the same. But I pulled the constant 3 out. So let's get to work on these product rule pieces. Hey, you know what? Look at this. Look at this first piece. Derivative of x cubed e to the x. We just did that. We actually just found it right here. So we're kind of doing a problem within the problem, and we already did some of those steps. So I know that this is going to get me I'm going to put parentheses around it just to kind of group things together. These parentheses are optional. Okay. That's what we get here. You can either get that by doing the steps all over again, or you could just notice that it's the steps we already did. This part, however, is x squared, so it could be different, right? It's not going to be the same thing as x cubed. So let's work on this. This is I've got a 3 on the outside, so I'm going to put parentheses. And we want the first function times the derivative of the second one. I know the derivative of e to the x is e to the x. Plus, I'm just doing this in my head right now. I'm thinking second function times derivative of the first. So e to the x times 2x. I'm just going to put the 2x out front. So are we done? Well, technically we did find the derivative, but you know, in this class, there's kind of it's kind of implied that we also want to simplify our answers. And we want to see, can we simplify this at all? I think I'm going to get rid of the parentheses and distribute this 3. So this 2 becomes a 6. The reason why it's important to do that is because then I notice, hey, wait a second, I have a 3x squared e to the x plus another 3x squared e to the x. Those can be combined, and they should be combined in order to get a simplified answer. So x cubed e to the x plus 6x squared e to the x plus 6x e to the x. Are we done now? Let's look at it. Is there anything else that can be combined? Well, not by addition, not by just adding stuff. So I'm going to say that we can leave the answer like this. Or, you know that I've been writing some of these today in more than one way. I think that this last step is optional. You could pull out x e to the x from every term. And then you would have x e to the x times x squared plus 6x plus 6. Either one of these answers is fine. The last way that we just wrote it is kind of nice because it shows it as like x times e to the x times a polynomial. Kind of reveals this polynomial that was sort of hiding in the problem. So that's kind of cool, but either one of these answers is fine. So that problem had us do the second derivative. If you got that right, then I think you're probably getting pretty comfortable with the product rule. If not, it's okay. We're still learning this, and we're going to see some more problems before we finish today. But for now, we are going to talk about the other rule. This section was supposed to be about the product rule and the quotient rule, so we need to talk about the quotient rule. The quotient rule. Again, this is going to be a formula that we derive, and then we can use it on problems. This time, the question is, if h of x, I used a lowercase h for some reason here. You could do it lowercase or uppercase. Either one is fine. If we have a quotient of two functions, that's a quotient of two functions. What is the derivative? Now, it would be really nice if we could just do f prime over g prime. Unfortunately, we can't. That's not going to get us the correct answer. You know, if you could just do derivative of the top, derivative of the bottom, that would be great. But unfortunately, it doesn't work that way. Doesn't get the correct answer. So we need to find a new rule. So here's what we're gonna do. I'm gonna take this, and I'm going to rearrange it to say f of x equals h of x times g of x. That's okay, right? All I did was multiply both sides by g. So this is just rearrange. Now I'm going to differentiate both sides. We're working on deriving something, so some of the steps, sometimes there's some clever little tricks, and differentiating both sides is going to help us. I'm going to say in parentheses, with respect to x. So sometimes we say that in math. To be clear, I'm going to differentiate both sides with respect to x. In other words, I'm going to do d dx of both sides. The left-hand side is going to become the derivative of f. The right-hand side is the derivative of a product. So I'm going to use the product rule. I'm going to have first function times derivative of the second one plus the second function times the derivative of the first one. Okay. Is this helping us? What are we trying to do here? We're trying to find h prime of x. Oh, look at this. H prime of x showed up in this step. Note, this is what we're looking for. Now we'll rearrange to solve for it. So we're going to just take all these 5 pieces, right? There's 1, 2, 3, 4, 5. We're going to rearrange the 5 pieces to get h prime of x by itself. H prime of x equals something in terms of these other pieces. So first of all, let's get the g of x times h prime by itself on one side of the equation. And that means the other side of the equation will look like this. H of x g prime. So we're rearranging, just algebra. Same pieces, just moved around. And now let's divide both sides by g of x. F prime of x minus h of x. All right, I said we were going to divide both sides by g of x. That's where we're at so far. Now, here's the thing. I don't really like that the formula that we've gotten. I guess you could say we found h prime of x. It equals this formula. I don't like that the formula has h in it. You know, it would be nicer if we could get an answer that just involved f's and g's, because the original problem was like there's f of x over g of x. So here's what I'm going to do. I'm going to replace h of x with f of x over g of x to get a formula that is just in terms of 2 letters, 2 functions. It's just in terms of f and g. That's a little bit nicer. Now the thing that bothers me about this formula is that it has a fraction inside a fraction. So there's a nice, clean way that we can deal with that. We're going to multiply the whole thing. In order to get the fraction out of the top, what could we do to get the fraction out of the top? We could multiply the top and bottom by g of x. As long as we multiply the top and bottom by the same thing, it's like we're just multiplying by 1, so we're allowed to do that. But it actually will make the numerator, in my opinion, it makes the numerator simpler because we won't have a fraction up there. So what we're going to get is g of x, f of x, minus f of x, g prime of x, over, the bottom is going to be g of x squared. Well, that's the formula. That's the formula that we call the quotient rule. And, you know, unfortunately, it's not as simple as we might have wished. But for solving this type of problem, I guess I can't fit the problem on the screen anymore. We scrolled it off the top. But you're trying to find the derivative of f over g. You have to do all of this. Oh, I'm missing a prime symbol. I'm sorry. Some of you probably caught that. Look at this. This g gets multiplied by this f prime. So this g should be multiplied by f prime. All right, I'm just going to point to this right there. I was missing a prime symbol for a minute. It's there now. So make sure you have that. So in order to find the derivative of f over g, we have to use the quotient rule, which uses this formula. It's the same four puzzle pieces that the product rule uses. It's like the function, the second function, the derivative of the first one, the derivative of the second one. We also have the second function getting squared down here. But we need to remember this order. One way that you could sometimes remember it, I've seen it written in this more compact form. I'm not going to rewrite this with the ddx notation because I think that would actually get kind of big and messy. But we could maybe write it in like a compact way. If this helps you remember it, gf prime minus fg prime over g squared. Keep in mind that when we say g squared, we're not talking about the second derivative. We're talking about it getting squared. So I think doing some example problems will help, but this is the formula we need to use. And we derived it. We proved it. So that's all the proofs for today. All right, let's do an example. Let's say we're given, I'll do this first one. Let's say we're given y equals 3x minus 1 over 2x plus 1, and we want to find y prime. And yeah, I don't think we could have done this before. I don't think we could have done this until now. We needed the quotient rule. So, you know how with the product rule, I was referring to the functions as the first function and the second function, f and g? For the quotient rule, I often refer to them as the top function and the bottom function. Makes sense, right? So what does this rule say? It says first we need the bottom function times the derivative of the top function minus sign top function times derivative of the bottom function. All of that over the bottom function squared. And I've added parentheses where I think they would help to group things together. But if you compare this with the quotient rule formula, we have all the correct pieces in the correct place. So look at what we still have to do. We have a ddx of 3x minus 1. That's a simple derivative. We can do that. And we have a ddx of 2x plus 1. That's a simple derivative. We can do that. So in math, we like it when we take a problem and break it down into smaller problems like that. So this is going to be 2x plus 1 times 3. And this is going to be 3x minus 1 times 2. All of that is still over 2x plus 1 squared. I'm not expanding that out. I'm just leaving it the way it is, the denominator. So there's no more ddx's in the answer. So in a way, you could say that we did differentiate and we did find y prime, and anything that's left is just considered simplifying. And I think there still might be some simplifying. What I'm going to do is I'm going to distribute what's up top. 6x plus 3 minus 3x times 2 is 6x. And then minus 1, 2. So this is going to get us a plus 2. And look at that. I'm glad that we did that last step because it shows me that there is a 6x minus 6x. And, you know, I couldn't see that in the previous step, but now I could see. 6x cancels with the 6x. 3 plus 2 is 5. So my answer is 5 over 2x plus 1 squared. All right, two things I want to say about the quotient rule before we do more problems. First thing I want to say is it still seems like it took a lot of steps, like it was a lot of work to do all this, right? However, it is still much easier than using the definition of the derivative. If you were to break out the limit as h goes to 0, of, you know, do all of that, for this problem, it would actually, that would be harder. So the quotient rule, even though it looks complicated, it is our best option for this problem. Another thing that I wanted to say about this is you have to make sure that you get these pieces in the right order. Notice that the quotient rule has a minus sign. Now, the product rule had a plus sign. And in math, when you add things together, if you put them in the other order and you add them together, you still get the same result, right? So in the product rule, it kind of felt like the order of pieces didn't matter so much. If you rearrange them, you still add them and get the same thing. That's not true for subtraction. For subtraction, you have to have them in the right order, right? 5 minus 3 is not the same thing as 3 minus 5. So you have to have the first piece first and the second piece second and a minus sign in between them. Don't mix up these two. If you mix up these two halves, the answer you get will probably be the negative answer of what it should have been. And you'd get partial credit for that. But if you want full credit, you know, get the pieces in the right places. Also, this simplifying step that happened near the end and gave us just a 5 at the top, that doesn't always happen. You know, it's nice when it happens, but we're going to see some other ones. Okay, so I'm going to do another one for us, and after I do the next one, then I'll have one that I give you to do. Let's say we're given, I'm going to have one that's called f of x. I think that, you know, just like with the product rule, we understand that the function could be called f. We could still refer to the quotient rule formula, but be careful about, like, this f of x in the formula is not, it's not this f of x, right? The f of x in the formula is supposed to be the top function. So just be careful about that. Top function and bottom function is how I'm going to refer to them. Let's see. So I said I was going to do this one for us. We're going to find f prime. F prime of x equals. So I need the bottom function times the derivative of the top one. And I put parentheses around this because if I don't put parentheses around it, Here, let's leave some space here and talk for a second. If I don't put parentheses, like you might look at the original problem and say there's no parentheses in the original problem. Why do I need to add parentheses? Because if you don't put the parentheses there, it would mean something else, right? If you don't put parentheses there, then you're not multiplying this entire thing by this entire thing. So put parentheses wherever you need to group things together. I wanted to make sure that the 1 plus x is treated as one object. The way we do that in math is with parentheses. Over here, I need the top function times derivative of the bottom. Derivative of 1 plus x, which I'll put parentheses around. It never hurts to have extra parentheses, by the way. And then on the bottom, 1 plus x, and that's getting squared. I put parentheses around it to make sure the entire thing gets squared. Notice that I do not need to write limit as h goes to 0 or anything like that, because we're using the quotient rule. The quotient rule does not have a limit. We're not doing a limit here. All right, what do we have here then? So 1 plus x times e to the x minus e to the x times 1. We've done all of the derivatives, and now we're going to see if anything cancels or simplifies. You know, that 1 there, we don't even need that 1 there. The 1 plus x times e to the x, I think I'll distribute across the parentheses, because that helped us last time. And I'm not writing times 1. It's okay to write times 1 in the middle of a problem, but as you get towards the end, you just get rid of it. Okay, look at this. We do have something that cancels. We do. Actually, in this one, the e to the x minus e to the x. Just like in the previous one, we had, what did we have? A 6x minus 6x? Anyway, I told you that doesn't always happen, but it's nice when it does. You get something that cancels, makes your answer look a little bit more compact. And that's going to be the answer. All right, so let me give you a problem to try. Let's see. For now, I'm just going to say find d dx of x over e to the x. All right, so take a minute and try that, and then I'll talk about it. Okay, so this one starts off, I mean, it looks relatively simple. It starts off kind of simple. There's something interesting that happens when we're simplifying it at the end. So, derivative of x over e to the x, this calls for the quotient rule. So I'm going to say top function, oh, sorry, I meant bottom function. I wrote the correct thing, but I said the wrong thing. Bottom function times derivative of the top. That's bottom function times derivative of the top minus top function times derivative of the bottom. All of that over the bottom function squared. Okay. Now I'm going to deal with the ddx's that are in this problem, ddx of x, ddx of e to the x, and I get e to the x minus x e to the x over e to the x squared. But don't stop here. We could simplify further. We could simplify further because I notice that every piece of this problem has e to the x. There's one there, there's one there, there's 2 on the bottom. So think of it this way. Up top, what would happen if you factored out e to the x? You get that, right? And on the bottom, we have e to the x squared. E to the x squared is really e to the x times e to the x. So we have something here that cancels. We have an e to the x over itself. So the final answer, in its most simplified form, can be 1 minus x over e to the x, and nothing is getting squared in the final answer. So I think the tricky part of that one was the simplifying. Sometimes that's how calculus is. Sometimes the derivative part is the hard part, and sometimes it's not the derivative that's hard, it's the simplifying. Okay, I've got a problem to show you. So far today, what we've done in this lesson is we derived the product rule, and we did probably about 3 problems. And then we derived the quotient rule, and we did about 3 problems of that. So we've seen a few problems of each, and I want to show you a problem that needs both rules. And I'll do this one for us. This is going to say differentiate f of x equals x e to the x over x minus 1. That's x e to the x over x minus 1. So we'll go through each step. So I'm saying this is going to need both rules because it looks like it's a quotient. I mean, there's the quotient bar, so it's definitely a quotient. But look at the numerator. The numerator looks like it's a product of two things. So which one do we do first? What do we do first? The truth is, you could probably rearrange this problem to do it in either order if you did it, carefully. But I think what I'm going to do is say, I see a quotient bar, and I'm going to think of this first and foremost as a quotient. So quotient rule first says bottom function times derivative of the top minus sign top function times derivative of the bottom. All of that is over the bottom function squared, where I added parentheses where I think they're going to help us group things together. So I used the quotient rule to get this far, but look, this right here, this is the piece where we're going to need the product rule. This little product, this d dx. Okay? So let's go through it. Let's say this is x minus 1 parentheses. Let's just go through this right now. Let's get it over with. The product rule, which we did earlier, would say you take the first function times derivative of the second. The derivative of e to the x is just e to the x. So let's just write that. Plus second function times derivative of the first. The derivative of the first function is, derivative of x is 1. Minus sign x e to the x times, what do we get here? D dx of x minus 1. The derivative of all of this is just 1, because the derivative of x is 1. The derivative of minus a constant is 0. It's just a constant. All right, all of that is still over x minus 1 squared. Okay, we actually did all the differentiating, right? There's no more d dx's. So now it's just a matter of, like, is there anything that cancels? Let's get rid of the times 1, and, like, let's just fix up the answer a little bit. How do we want to do this? I think, do we want to distribute? I actually think instead of, distributing this times this, I actually think I want to pull e to the x out. I see e to the x and e to the x. You know, when it comes to algebra, sometimes you have some choices to make. I'm choosing to do it this way. Like, that's what I'm turning that whole piece into. I pulled e to the x out. I still have the x minus 1. And then what am I left with in this set of parentheses? In this set of parentheses, if I pulled e to the x out, then I'm left with x plus 1. And then over here, we have minus x e to the x. All of that is still over this squared. Let's see if we can go any further with this. Let's see if anything cancels or... Let's see. Well, look at this. Look at this. X minus 1, x plus 1. That actually combines to be x squared minus 1, doesn't it? It factors, you know. X squared minus 1. This, you know, this factors out to these two factors. So we have this minus this. Okay. I think we're going to need to continue this on another sheet. We're almost done. Maybe 2 more steps, though. 1 or 2 steps. We'll see. All right. What I've got here is... x squared e to the x minus e to the x minus x e to the x over x minus 1 squared. Right? All we did was distribute across those parentheses. What if I factored out e to the x now? What if I had e to the x, x squared minus 1? Or, you know what? It's going to be minus 1 and minus x. With polynomials, if we're going to have a minus 1 minus x, we kind of prefer to write the x first, don't we? Let's write it like that. So this is where we're at right now. I'm going to move the page up. This is where we're at. All right, so the thing that I have in the numerator, I'm looking at that and I'm thinking, does that factor? Does that factor nicely with like whole numbers? And unfortunately, it doesn't. It doesn't factor nicely. So we just leave it, right? What do you do when something doesn't factor? You just don't factor it. You leave it. So I'm going to say that for this problem, this is a good answer. Or if you wanted to stop a step earlier, that's fine too. Either one of these is good. We went pretty far with simplifying it, so I'm happy with either of those. The reason why I took it this far in simplifying and I tried to factor, I got here and I was like, oh, well, can I split this up into 2 things? You know, the reason I did it was because I was thinking, what if this factors and one of the factors might be x minus 1? If this factored into x minus 1 times something, then we'd have an x minus 1 over this and we'd be able to do some canceling, and that would be really nice. That sort of happened in the previous problem with an e to the x canceling. So I was actually looking at this and I was hoping that we would get an x minus 1 to cancel, but we don't, so we just leave it. So that was the biggest problem we did today. We had to use both rules. So I know this has been kind of a longer video, but before we go, I want to have you do a couple of practice problems, because the product rule and the quotient rule, we're going to be using them all semester. I don't think that's an exaggeration. We're going to be using these rules that we learned today all semester. I mean, the good news is that you're going to continue to get practice in the next section and the one after that and the one after that. But, you know, we're going to start doing other things with them. I'd like you to get in a couple more practice problems today before we move on. So I'm going to give you a part A and a part B. And, you know, you'll also have homework on this to practice, and you can find other practice problems. Okay, go ahead, take a couple of minutes and see if you can get these. All right, so hopefully you paused the video and you tried those. Let's work on these solutions. So for part A, I'm looking at this as the first function and the second function. You could think of them as f and g if you'd like. So first function times derivative of the second one plus sign, because we're doing the product rule. Second function times derivative of the first one. I know what that derivative is going to be. We could have just differentiated as we go. That would be fine. All right, so y prime is e to the x times, what's the derivative of this polynomial? You should get 4x minus 3. And then over here, we still have 2x squared minus 3x plus 5 times e to the x. We differentiated, but now we want to see if anything cancels, if anything combines. You know, I have a feeling that between these two pieces, there might be something that combines. So let's distribute. So let's write this as 4x e to the x minus 3e to the x. And let's distribute here also. 2x squared e to the x minus 3x e to the x plus 5 e to the x. And then we look for things that are the same type of term. 4x e to the x looks like that can cancel, not cancel, but it can combine with this, right? I'm going to underline it. This and this, they almost cancel out, I guess. But yeah, combine them into just x e to the x. 4 minus 3 is 1. I also see this minus 3x can be combined with this plus 5 e to the x. We have minus 3 of them, and we have plus 5 of them, so we have a total of plus 2 e to the x's. And then the only thing we didn't underline, it just kind of stands by itself, is this term. So you could leave the answer like this. Or another way that I found the answer is I got to here and then I factored out e to the x. You could do that if you'd like. 2x squared plus x plus 2. Either one of those is fine. So let's talk about part B. Part B is going to use the quotient rule. And we might have to be careful about pluses and minuses when we're doing the quotient rule. Okay, y prime equals bottom function times derivative of the top minus sign top function times derivative of the bottom. All of that is over the bottom function squared. That's a good start, but we still have a lot more to do, right? What's d dx? Let's look at each of the little derivatives here. So like d dx of x minus 3. The derivative of x is 1. The derivative of minus a constant is 0. So this is just 1. This whole derivative right here is 1. So we just say 2 minus 5x. You know, there's kind of a times 1, and we don't have to even write that. And then we have the x minus 3 that was already here. And then let's figure out what this is. Derivative of 2 minus 5x is minus 5. All right, it's not so bad. Let's try to fix this up and see if anything in the numerator is going to cancel. So that first set of parentheses I don't even need. Around the 2 minus 5x. Let's just get rid of it. No parentheses there. And then let's distribute here. This is where you got to be careful about pluses and minuses, right? So minus, there's this x getting multiplied by minus 5. So we're going to get plus 5x minus 15. Why is it minus 15? It's a triple negative. There's minus 3 minus 5 gets us minus 15. Just be careful about the algebra stuff and arithmetic. Hey, look at that. We have something that cancels. We have a 5x and a minus 5x. And the 2 and the minus 15, they don't cancel, but they definitely combine with each other. 2 minus 15 is minus 13. So that is much simpler than what we had 1 or 2 steps ago. And that's a good answer. I think this is probably about the only way that you could get, the only way you could write the answer. The only other thing you could really do to this is you could expand the denominator. But I don't think that's going to make anything any simpler. So I wouldn't bother doing that. You notice that in the quotient rule problems that we've done, we typically leave the denominator in this form. It's really the numerator that we work with the most. The denominator is just something squared, unless you get lucky and find something that cancels near the end of the problem. All right, I'll give you one more moment in case you're copying any of that, and then we're going to wrap up soon. All right, so I know this has been a long video, so I'll try to keep this short, but the product rule and quotient rule I consider very important. What we're going to be doing next in this course is we're going to have a few lessons where we're still doing more derivative rules. There's kind of a big third rule, product rule, quotient rule, and one other that we're going to get to soon. It's called the chain rule, but we'll get there very soon. I think 2 videos from now. But we're going to establish all these rules about derivatives, and then we're going to be able to differentiate almost anything we want. And then where we're headed in this course is that then we will start seeing some more applications of the derivative. Like what else, like what can it be used for besides just slope of the tangent line, and besides like velocity and acceleration? What else can we do with the derivative? So that's where we're headed, and that's why we need to be really good at differentiating. Okay, so that was my 1-minute speech, and that's going to be it. So hope everyone is doing well, and I'll see you soon.